Welcome back to our class. Let's continue our discussion for the key technical challenges to optical communication in the next decade. In this new chapter, we will continue to discuss the second chain of key technology development. Besides the C-band, how much new spectrum can we use for optical communication? From the introduction in the previous section, we already know that expanding the available spectrum is one of the two main ways to increase the capacity of long-haul optical network systems. So, does this mean that we can expand the spectrum unlimitedly in order to expand capacity? And what are the limitations of this expansion? Before we answer this question, let me briefly introduce you the spectrum that is often used in optical communication network first. Some of the known electromagnetic spectrums, such as gamma rays, it is harmful to the human body, and X-rays, which are often used in physical examinations, ultraviolet rays used for sterilization. These are short electromagnetic waves, while the common spectrum of a telecommunication network includes a spectrum used for wireless communications. It ranges from 300 MHz to 300 GHz, and it is an electromagnetic wave with long wavelengths. Optical communication uses the spectrum with wavelengths between the two mentioned above. It is invisible light located in the near-infrared region, and we use only a small part of the whole electromagnetic spectrum. Currently, the most commonly used spectrum for optical communications range from 1260 nanometer to 1625 nanometer. We are used to divide them into O-band, E-band, S-band, C-band, and L-band. Among them, 1310 nanometer was first used in SDH networks and later extended to post and other client-side interfaces. It is the most commonly used spectrum in optical communications, except for WDM systems. 1271 nanometer to 1611 nanometer. It is used for coarse wavelength division multiplexing systems. It is also called the CWDM wavelengths. They have 20 nanometer spacing between the two channels. 1550 nanometer. It is used in dense wavelength division multiplex systems, which is also called the DWDM system. It has a channel spacing of 0.4 or 0.8 nanometer. Other common spectrums used in optical communication include 980 nanometer and 1480 nanometer. Both of them can be used in EDFAs or erbium doped fiber amplifiers. 1491 nanometer, 1511 nanometer, or 1510 nanometer may be used as a wavelength for optical supervisory channel. Next, let's focus on the wavelengths used by the WDM system. In fact, if we look at the 1200 nanometer to 1600 nanometer spectrum, the total usable spectrum is 400 nanometer. But how much are we using now? From the previous section, we know that the traditional C-band is most commonly used on the live network. The spectrum ranges from 192.1 THz to 196.0 THz. The total spectrum is 4 THz. It is about 30 nanometers. In the past 2 years, more and more operators have started to use the extended C-band, 4.8 THz, and Super C-band 6 THz solution. These two parts are only about 1/10 of the 400 nanometer, and the rest of the spectrums remain to be explored and developed. Our medium and long-term evolution goal is to break through the full spectrum amplification boundary. First, we expand the available spectrum of the C-band at 48 nanometer to the C-band plus the L-band at 96 nanometer, and then further expand the spectrum to the S-band, U-band, and E-band. Here, you may wonder, we have a total spectrum of 400 nanometers, and we are currently using only a small part of it. Why isn't the expansion of the new spectrum as smooth and simple as we thought? What's holding back the use of new spectrum? To expand the available spectrum, it requires the support of various new components. These components including new tunable lasers, new optical amplifiers, new WSS components, new spectrum analysis boards, protection boards, and variable optical attenuators. New tunable lasers are needed to output and receive wavelengths of new frequency bands with stable and high precision. A new optical amplifier is used to amplify the extended full spectrum signals and provide stable gains. A new WSS component, that is a wavelength selective switch. It is used to flexibly groom new wavelength signals in different directions. In addition, because the single wavelength rate has exceeded 800 gigabits per second and 1 terabit per second, flexible spectrum allocation is required for a single channel. Therefore, the wavelength selective switch needs to support flexible grid wavelength grooming. In addition, new spectrum analysis boards are used to monitor the wavelength performance of new spectrum range. Among these, new optical amplifiers are the most important technical obstacles and challenges to the expansion and use of new spectrums. So why is it so difficult to use new optical amplifiers? First, let's review the working principle of traditional optical amplifier first. Traditional optical amplifiers include erbium dot fiber amplifiers. This is also short as EDFA, and Raman fiber amplifier. This is short as RFA. We will take the EDFA as an example. The operating wavelength of the EDFA is 1550 nanometer window, which is exactly the same as the low attenuation window of the fiber. That is, the gain spectrum of the EDFA overlaps with the lowest attenuation band of the fiber transmission. It can cover the entire C-band range from 1530 nanometer to 1565 nanometer. The working principle of the EDFA is like this. The input signal light and the pump light emitted by the pump laser are multiplexed by the multiplexer and then enter the erbium dot fiber EDF. The erbium dot fiber EDF generates amplification under the excitation of the pump light. Therefore, the input optical signal is amplified. The essence is to utilize the electron energy difference of different energy levels around the erbium trivalent ion, and the pump line provides energy to excite low energy level electrons into high energy level electrons, while the high energy level electrons are unstable and transition to stable state. At the same time, photons covering the wavelength range of 1550 nanometer are released to amplify the input signal light. Because the energy difference between the two levels exactly equals to the energy of photons with a wavelength of 1550 nanometer, EDFAs can only amplify optical signal in the wavelength range of 1550 nanometer. The C-band and super C-band, which are extended on the basis of original 4 terahertz, require some special processing for the EDFA. For example, we need to dope other elements, but the basic principle is still energy level transition. In the future, if we want to break through the O-band, E-band, S-band, and L-band, these new bands, and achieve a usable spectrum of 400 nanometer. We need to continue to study the elements, dope into fibers, and find a stable production process. After decades of research and development, the gain and bandwidth of traditional optical amplifier doped with natural elements have reached the limit. Now we focus on the development of future optical communication. In addition to continuing research on traditional optical amplifiers, the industry is also actively researching some new optical amplifiers. There are currently two research directions. The first direction is miniaturization and high integration. The traditional EDFA is replaced by a semiconductor optical amplifier, SOA. The principle of SOA it is actually similar to that of EDFA. It has the advantages of simple structure, small size, full use of exciting semiconductor laser technology, mature manufacturing process, low cost, long service life, low power consumption, and easy integration with other optical components. Because SOA can use wavelength in excess of 100 nanometers only by changing the composition of the semiconductor material used. This is a promising research direction for expanding the available spectrum of optical communications. The current SOA needs to solve the following problems. The coupling loss between the SOA and the optical fiber is too large. The noise and crosstalk are large, and the SOA is easily affected by the ambient temperature, and the stability is also poor. This is also the direction of subsequent SOA research. The second direction is to study new amplification mechanisms that can realize ultra-low noise. Currently, quantum dot optical amplifiers and phase-sensitive optical amplifiers are mainly studied. The quantum dot refers to a quasi-zero-dimensional semiconductor nanograin with a size of 1 to 100 nanometers. The quantum dot has good optical gain and amplification characteristics, and the size of quantum dot can be adjusted artificially to change the absorption and emission spectra of the quantum dot, so as to adjust that peak wavelengths of absorption peak and radiation peak. In recent years, both at home and abroad have actively invested in the research of quantum dot optical amplifiers, and some breakthroughs have been made. For example, some studies have shown that a multi-doped quantum dot optical amplifier has extremely wide bandwidth and very low noise. With a gain of more than 20 dB, the flat bandwidth of -1 dB can reach 120 nanometer, and the noise figure is as low as 3.3 dB. The performance of the EDFA is far superior to that of the conventional EDFA. Right now, it's expected to become the main amplifier of the optical fiber communication system in the future. Currently, quantum dot optical amplifiers need to be further studied and explored. For example, how to improve stability and reduce noise figure, and how to make quantum dot optical amplifiers out of the laboratory to achieve productization and commercialization. Lastly, let's make a brief summary. In this chapter, we discuss the second trend and challenge in optical communications over the next decade. What spectrum can be expanded beyond the C-band and how to expand it? First, we review various spectrum used in the optical communication networks. Then we briefly introduce the future expansion evolution ideas. Finally, we use an example of an optical amplifiers to explain the obstacle to spectrum expansion and the direction of research breakthroughs. That's what we have covered in this section. Next, let's use two simple questions to consolidate the content of this section. First, it is a single choice question. Which of the following statements about the available spectrum for optical communication is incorrect? A. SDH network mainly uses 1310 nanometer. B. Currently, DWDM network mainly use 1550 nanometer. C. Optical supervisory channel can use wavelengths of 1491 nanometer, 1511 nanometer, or 1510 nanometer. D. The erbium dot fiber amplifier can use 850 nanometer or 980 nanometer as the pump light. We have introduced that the SDH network mainly uses 1310 nanometer, while the DWDM system mainly uses 1550 nanometer. So A and B is correct. C is also correct. D. EDFA use 980 nanometer or 1480 nanometer wavelengths as pump light. Actually, we have mentioned 850 nanometer is not the pump light. So the answer is D. The second question is a multi-choice question. Which of the following new components need to be introduced in the expansion from the traditional C-band to the super C-band? A. New laser. B. New optical amplifier. C. New wavelength selective switch components. D. New spectrum analysis board. E. New tributary board. According to the previous description, we know that lasers, optical amplifiers, WSS components, and spectrum analysis boards are all required, but tributary boards are not required. Client port is the same for Super C-band solution, so the correct answer is A, B, C, and D. Well, that's all for this chapter. Thank you.